Okay, today I want to continue with yesterday's lesson and talk about the constancy of the speed of light a little bit more, and then maybe do a sample problem or two using the velocity addition equation. Um, we Yesterday we decided that Einstein's two postulates of relativity were: number one, all laws of physics work in all reference frames, which I mean obviously should be true. And the second postulate was the speed of light is a constant in vacuum in all reference frames. It's always c, no matter what. Um, and if we accept that as a true postulate, then Galilean relativity can't possibly be true. And then Einstein had to rederive the velocity addition formula. Now, let me kind of give you a little background here as to the constancy of the speed of light and issues they were having with it at the end of the 1800s and the early 1900s. Light is a wave, electromagnetic wave from James Clerk Maxwell. But waves need a medium through which to travel. Without the air, sound waves can't travel, and there's no sound. Without a jump rope, there's no wave to be sent through. So you need some physical medium through which a wave can travel. Okay, that's fine. Light travels through the air. The air is a physical medium. But light also travels through outer space, and there is no physical medium there. So how does light from the sun get to us if it's a wave and space is empty and there's no stuff there to wave? What they came up with during the 1800s was a concept called the luminiferous ether. You see it down here spelled A-E-T-H-E-R. It comes from the same Latin root word as we get ethereal from, ghostly. So they figured space we think is empty, but in reality they believed, they were wrong in this, but they believed space must be actually filled with some ghostly, mysterious stuff called the ether. And that ghostly stuff is what is the medium that light waves are traveling through. So, okay, great. It's a theory. We can't detect it, but whatever. Sooner or later, those people started realizing that, wait a minute, if that's true, then there must be an absolute rest frame. There must be some reference frame that's not moving relative to the ether, whatever that frame happens to be. The Earth is almost definitely not it. We're not the center of the universe or anything like that. So the Earth, as it moves around the sun and as the sun moves around the galaxy and so on, must be moving through the ether, which means there's an ether wind blowing past us. Just like if you run into the air, you get a wind blowing in your face. Now, that matters because light traveling through the ether wind should be sped up or slowed down if it's going with or against the wind. And so these two guys, Michelson and Morley, came up with an idea to do an experiment to try to find that ether wind and prove that the ether must exist. The basic idea is this. They're going to take a light beam starting over here and shine it at this mirror, which is a partially silvered mirror. What that means is when the light hits it, some light will reflect, some light will pass through and go straight. Now, there's mirrors here and here, so when the light passes through, it bounces and comes back. When the light reflected bounces, comes back. Both are going to recombine here and go to the detector over there. Now, notification, great. Let's assume that the distances here and here are equal, and run the simulation of Michelson-Morley's experiment. The light waves coming in, slow down obviously, hits the mirror, some reflects, some goes through, bounces back, and they come back and hit at the same time, and they come back in phase. So the two waves hit simultaneously, crest and crest lined up, meaning you end up with a bright light source there, or a bright light appearance there on the detector. Now, if I were to move one of these mirrors around, the waves would no longer line up, and as you moved it, you get bright, dark, as the wave crests get in and out of phase. But let's, for now, leave them lined up like that, so we can adjust the distances and look and make sure they're lined up. Now, what about, though, if we're really moving through an ether, this mysterious stuff, there's an ether wind? Well, let's create an artificial ether wind here. I'm going to make it pretty big. So, notice the ether wind is blowing upward. So that means the Earth must be moving down on my diagram here as it moves around the sun and so on. So Now, if we rerun the simulation, we're going to see the light wave going with the ether wind speeds up. But when it comes back against the wind, it slows down. Meanwhile, the one that goes straight across isn't going to be affected. So let's see how that affects their, what they do when they recombine. Light wave coming in, hits the mirror, splits. See how the red one hits first, but now it's slowing down. And they don't come in phase now. They're out of phase. Crest hits, trough hits, crest hits. So they're out of phase. You're going to get darkness instead of brightness. Okay? So you can detect the ether wind. Now, notice in this case, we wouldn't know whether there was a wind or not. So how they figured they'd test this is run the experiment once and then rotate the whole apparatus. So if it was perfectly in phase when I ran it first, when I rotate it, it should be out of phase now because the different side is lining up with the ether wind. And so now it should, where it was bright, it should be dark. The waves will no longer line up. Problem is, a group chat. Problem is, when they tried the experiment, it didn't work. No matter how they rotated the apparatus around, they never ever detected an ether wind. So they believe they failed. Their experiment failed to detect what they were looking for. But what Einstein said, actually, you succeeded in proving my point. The speed of light is a constant, whether there's an ether wind or not. And by the way, since it's impossible to detect, why even bother? Let's just say it's not even there. But if there was an ether wind, then that would make the speed of light speed up or slow down, violating that whole constant speed of light thing. And since the experiment clearly showed that speed of light is constant no matter how you turn the device, no matter whether there's an ether wind or not, and there's not, but it showed that Einstein was correct to assume that the speed of light is indeed a constant and always equal to c. So I wanted to show you this Michelson-Morley experiment because it's one of the foundations that verify that relativity is correct in picking that postulate, speed of light is constant, rather than picking the velocity addition postulate from Galileo, which on the surface seems more logical. But we have experimental proof or experimental evidence, I should say, showing that the speed of light has to be constant. And therefore, the logical velocities just add like normal addition can't be true. And so we had to come up with that adjusted equation. So with that behind us, let's come to my whiteboard. And looks like I got about half my time left, so I can do this. Remember, we did u prime equals, oops, this is a terrible equal sign, equals u plus v over 1 plus uv over c squared. Okay, so v is the velocity that the one frame is moving relative to another. Okay, I'm in my spaceship and there's an enemy spaceship charging at me at velocity v. So the enemy's reference frame is moving at v relative to my reference frame. They think they're at rest and I'm moving. I think I'm at rest and they're moving toward me. Whatever, both work. Now they fire a missile at me at speed u. Okay, so normally you'd say, all right, well, the missile is coming at me at u plus v, their speed plus the missile's speed. But if it's near the speed of light, then you have to adjust it for this denominator down here. And now, let me show you a quick example of that. I mentioned yesterday, not in the lecture, but in the text I put with it, that it's often useful to express your velocities in terms of c, and that way the c's cancel. So for example, let's say that an enemy spaceship is charging toward me at 0.5 c, half the speed of light. So that's v. I'm sitting still in space in my reference frame, and the enemy Klingon ship or whatever is flying toward me at half the speed of light. Okay? Now, let's say now they fire a missile at me, and the missile they fire at me is at 0.7 c from their reference frame. I'm only doing one sig dig here because I'm being lazy, but whatever. So the Klingon commander is firing the missile, and he sees it zipping away from him at 0.7, 70% of the speed of light. So that's U. It's the velocity of the missile from the enemy ship's reference frame, the Klingon's reference frame. In my reference frame, what do I see? Now, notice if I were to use the old-fashioned way of just adding the two together, I would get 0.7 plus 0.5 is 1.2 C. So I would get the missile coming at me at faster than the speed of light. Clearly, that's not possible from what we talked about earlier. Nothing can exceed the speed of light. So we can't use the old formula. We have to use the new formula. So let's plug into that. U prime is going to equal U plus V. Now, U is 0.7 C. Notice again, I don't calculate how many meters per second that is. I don't really need to. I can leave everything in terms of C because you'll see things cancel out real nicely. Plus the velocity that the frames are moving relative to each other. In this case, their ship is coming at me at half the speed of light. So their frame is 0.5 C compared to mine. 0.5 C. So again, if that's all we did, that's Galilean relativity there, and that would give us 1.2 C. But Einstein realized we have to divide that by a denominator of 1 plus, now, 0.7 C times 0.5 C divided, and that's U times V, isn't it? And then divided by C squared. That's the relativistic adjustment term. Now let me scroll down so I can finish the problem. So U prime equals 0.7 plus 0.5 is 1.2 C, which we would have gotten with Galilean relativity, divided by 1 plus, now, 0.7 times 0.5 is 0.35, right? C times C is C squared. Divided by C squared, all the C's cancel. So we get 1 plus 0.35. You see the value of using units of C rather than meters per second. I can just let the C's cancel, all the speed of lights cancel. And that leaves me with just a number on the bottom. So up top I have 1.2 C, that's a unit of velocity right there, which I could sub in for meters per second if I wanted to. On the bottom, all the units cancel, leaving me with just a pure number. So now I can just add this all up. U prime equals 1.2 C divided by 1.35. And notice that the denominator is always going to be greater than the numerator. So when I divide these, which I'm going to get my calculator and do that, 1.2 divided by 1.35 equals, I get 0.89 C. So the missile is coming at me at 89% of the speed of light, not at greater than the speed of light. That's how relativity works. Now, notice if I were to plug in bigger numbers, maybe have them launching the missile at me at 0.9 C. Sure, it makes the numerator bigger, but it's also going to make the denominator grow even more. And I'm always going to get point something C. Okay? In fact, the largest case you can get is if you plug in the speed of light for something. Like I think question 3 or 4 on the worksheet I gave you was I was shooting a laser beam at you where U was equal to C, not 0.5 C, just equal to C. And you'll see when you go through those, you'll always come out with your answer equals C in that case. And I'll let you do that on your own to get a feel for it. I think what I'll do here is make that worksheet that I assigned yesterday, make that due at the end of today. That gives you a chance to now take this sample problem I did and apply it to what you've been trying to do yesterday and make sure you got it all right. So I'll post sometime later in the day an answer key showing the answers I got and make sure that you see that you agree with it. Once we're okay with this, then we'll move on to a cool thought experiment that Einstein does to show that time has to be relative as well. But that's a future U problem. All right, I'll leave it at that, and we'll talk again tomorrow.